Hello, everybody. Welcome to another discussion in dynamics. Without further ado, let's start because we have quite a lot of things to do. And to be honest, I didn't finish the second problem in 1 hour ago. Yeah, so I'm not sure. We will see. We'll see how it goes. Of course, if I didn't finish it, I will just record the video. Yeah, I'm gonna volunteer. Why not? I have nothing to do, of course. Yes, I'm not a busy man. So we'll record the video with the remaining part of the problem. Yeah, but we'll see. Okay, plan for today. Brief lecture review. And today we'll start a new topic, kinetics of particles. Okay, so for the first time, I just would like, guys, I would like you to think for a second about every single problem we were talking so far. Have we ever talked about mass of the particle? Yeah, today is the first time we will include mass in our solutions. Okay, previous problems were only about geometry. Yeah, different trajectories of different geometry, and so on. We knew that motion was happening, but we didn't know why. Yeah, we just knew that somebody told us that, hey, thing is moving. That's all. Yeah, like that. Today we will talk about the cause of motion. Yeah, which is force, for the first time. And we'll do, Professor Sony asked us to do example number 1 and 2. And example 2, the last part of that example is a little bit scary. It's a little bit monster, in my opinion. So I want to get there, okay? But if we want to get there, I will just record the video for you, okay? I will send you an email with a link and so on. Okay, and I also think that students sometimes like to see the course content. So we will see this diagram a lot. So in this course, we'll cover 8 topics: kinematics, kinetics, work energy, and momentum of particles. This is the first part of our semester. And then we will just repeat exactly the same four topics, but this time for rigid bodies. Okay? And as you can see, we are going to start new topic, kinetics of particles. So we can just cross out this day. Yeah, we are done with kinematics of particles. Today, kinetics, new topic. Questions so far when it comes to logistics? We good. Brief lecture review. So this is what Professor Sani talked about yesterday. He said that we have a particle of mass m, yep, here, and there is a force acting on that particle, force F. And that force will cause acceleration of that particle. Yes? Yeah. And by the way, that particle will accelerate exactly in the direction of force. F and A are parallel so far. Okay, in this part of the semester, F and A are parallel. That's all. That's the lecture review. Yeah, and we are going to use this thing to solve our 2 examples. By the way, on free body diagram, we show forces acting on our particle. On kinetic diagram, we show accelerations. Okay, I just want to systematize our solution steps. Okay, I want to save some ink, so I'm not going to write free body diagram. I'm just going to write FBD. Okay, and I'm not going to write kinetic diagram all the time. I'm just going to write KD for the same reason. Okay, and now you can clearly see that FBD is related to KD via this formula. F equals to MA. Forces on FBD, accelerations on KD. Actually, not accelerations, inertia forces, yeah? Inertia forces on kinetic diagram. Questions? Example number 1? We can do example number 1. Let's do it. As usually, please familiarize yourself with this this is like a novel, yeah? Please familiarize yourself with that novel before we start our solution. And I numbered them, yeah? So this is number 1, number 2. So this is number 2. Number 3 is the drawing, and number 4 is this drawing. Okay, so keep that order. All right. So what do we have in here? First of all, they told us to assume something that is not true in reality, okay? They told us to assume that this is rest length. So basically, if we have a spring and platform, they told us that after placing the platform on the spring, this is rest length. I mean, they didn't say it to us. They told us to assume it, yes? Of course, it's not true in reality. Let me switch the board very quickly, okay? This is what happens in reality, yes? Spring without platform has length of its rest length, yes? And after we place the platform on the spring, we have a little bit of pre-compression. Yeah? This is what happens in reality. Do you see that, guys? Yeah. However, they told us that, assume that this is rest length. Just assume it. And we will do it. Yeah. Assume this is rest length. This is rest length. Okay. That's what I wanted to clarify. That's why there is so much text in here. Anyway, what do we have? Okay, we have our spring that is at its rest length. And we have our particle M, particle of mass M. We're going to place it gently on the platform, and we will see what will happen, okay? They ask us to find maximum reading of the scale after that gentle placement, plus they ask us to find the maximum speed of the mass. Okay, and what do we know? We know the weight of the particle. We know that system starts from rest, and we know that the spring is linear. Okay. Any questions to the problem statement? If not, let's start our solution. Two parts A and B simultaneously. And I think that I'm not going to surprise you guys if I start with free body diagram and kinetic diagram. Yeah. Free body diagram and kinetic diagram. Yeah. And one more time, I'm going to save some ink. Instead of free body diagram, I'm going to write FBD and in here KD. Okay, so our particle will be represented here with this rectangle, okay? What forces act on our particle? I believe that we have mg. And what is the other force acting on our particle? Spring, yeah, exactly. Kx. And let's maybe define this direction as positive, okay? So we have M, MA. Okay. So as you can see, guys, FBD has to be balanced out by KD. Second step so this is first step. Second step of our solution is equations of motion. Equations of motion. But this is a waste of ink. Let's from now on write EOM, okay? Every time we talk about equations of motion, we will do EOM. Okay, so sum of forces in this direction, yeah? And this is positive direction. So I believe that mg acts in the positive direction and kx acts in a negative direction. And this is equal to ma. That's it. Okay, so I hope, guys, that you can see that FBD and KD, these drawings, they correspond to this equation. Do you see it? Yeah. Attendance. All right, so let's find acceleration. Any questions to what happened so far? Questions? Okay, let's find acceleration. So A is equal to G minus Km. Oh, X, not X. Y. Let's put Y here, okay? Sorry, guys. Instead of that X, let's put Y. Yeah, because it's like, you know, why we, so also I must correct that drawing, yeah? Yeah, ky, not kx. Y represents our deflection. Okay, so, and I want to integrate, yeah, because they ask us to find max speed and max deflection, let's say, yeah. So we are on accelerations level. We should go to, we should integrate. And by the way, our acceleration is expressed as a function of position. So I believe that this formula is useless for us, dv dt. Maybe it's not useless, but let's modify it a little bit, okay? Let's do that little trick we were doing. dv dt, dy, dy, yeah? So our A is equal to v dv dy. We're gonna integrate along the trajectory. V dv dy is equal to g minus km y. Okay, everything with v on one side, everything with y on the other side. V dv is equal to g minus km y dy. Let's integrate. And when it comes to integration bounds, I believe that our system starts at deflection 0 and it starts at rest. Yes, and we will end up at some deflection y with some velocity v. Okay, these are our integration bounds. Let's integrate. 1/2 v squared, and this is equal to gy minus 1/2 km y squared. Perfect. We have our equation of motion on the velocity level. So what now? Aha, what was part A? Aha, they ask us to find maximum reading. And maximum reading will be obtained for maximum displacement. So maybe some of you guys can tell me what is the requirement for maximum displacement? Anybody? What is the requirement for maximum displacement? Brian? Excuse me? The net force will be 0. But in here we don't have any more forces anymore. I see you guys, yeah? I want a lady there. Velocity will be 0, exactly. Are you Christina? Yes. Oh, wow. You look different than last time. Oh, glasses, yeah. Yeah. Okay, exactly, yeah. The answer is velocity 0, yeah. This is our requirement. So I can take this expression, but don't worry, Brian. 0 is equal to g y max minus 1/2 km y max squared. I want to talk to Brian for a second. Yeah, listen, do you know, because I noticed that I'm doing that like 6 times, that discussions, you know, and sometimes when people like, you know, want to help me here, yeah, and they're wrong, they're like kind of sad, yeah, afterwards. You're not sad, yeah, you don't care that much, yeah, don't worry, yeah. But do you know that it's good to make mistakes actually? Okay. Because there is only one group of people that don't never make a mistake. Only one group of people. Do you know who these people are? Yeah, these are people who don't do anything. Yeah, these are people who don't try at all. Yeah, they just sit in the chair all day and that's all they do. Yeah. So once you do anything, once you are active here, you are going to make a mistake. Yeah, but don't worry. I make 7 mistakes per day at least. Every single day I make 7 mistakes in my work and also in private life. Don't worry. Don't ask anybody. Yeah, okay. Yeah. Okay. Now we can go back to our, yeah. So don't worry, guys. Be active. Don't worry if you're wrong. It happens. Yeah. Life. That's life. Yeah. Okay. So we are at this equation. So I think that y maxes can be simplified. Yeah. And we obtain our maximum deflection. Y max will be, I believe, 2mg divided by k. Yeah, that's correct. Okay, so this is our maximum deflection. And our F max, this is what they ask us for, max reading reading is f max, and this is equal to k y max. Yeah, so just plug y max in here, and we will obtain k times 2mg divided by k. Oh wow, so that k can be cancelled out, yeah? And it's 2mg. F max is equal to mg. Interesting, isn't it? The maximal reading of the scale is twice as much as we weight. Yeah, so every time you walk on the scale, it will actually, the maximal reading of that scale is twice as much as you weight, guys. Interesting? Yeah, but it still shows the correct value. Yeah, I mean, I hope it shows the correct weight of me. Yeah, and you. Okay, that's the end of part A. Any questions? Answer. Easy so far? We are on the same page? Yes? Okay, so now part B. And I honestly forgot what they were asking us for, okay? Part B. I must scroll up the board, okay? Because I really forgot. Okay, max speed of mass M. Max speed of mass M. So I think I found that by taking this expression. Yeah, find max velocity, okay? So in here, we have velocity, kind of, we have velocity expressed as a function of position, yeah? So we have a velocity as a function of position. Do you remember from calculus, when they were asking you to find the maximum value of the function, what you were doing? Take a derivative over whatever the variable is. Exactly. And I don't know your name, sir. Sam. Okay. Thank you, Sam. So we're gonna do d over dy. Yeah, and we'll see what will happen. So in here we have, I believe, v dv of dy. And this is equal to g minus kmy. Yep. And Sam said that this value is 0. This value is 0 for at max speed. Yep, this is what he said. So I think that we can write something like that. 0 is equal to g minus km y obtained at velocity max. Okay, and we can see that y at velocity max is equal to mg divided by k. Okay, Sam, do you mind if I ask you for the next step? Yeah. Perfect. Here. Exactly. Thank you, sir. Yeah. So we have, so Vmax will be a square root of 2gy Vmax minus kmy at Vmax square and square root. Okay, guys, just plug this value here and here, okay? Plug this value here and here at home. Oops. Plug this value here and plug this value here. Okay, and you will obtain that our Vmax, after a couple of algebraical transformations, our Vmax is equal to exactly g m divided by k square root. This is answer part B. All right, and time for questions. Interesting. Anybody has any question? Thanks, Rob. Okay, we good? How about those problems? Are they fine with you guys? Yeah. I hope you also like the style of this discussion, yeah, because you already observed that I just do certain chunk of the problem, then you have time for questions, yes? Then we do more, you have time for questions, yeah? And then we finish the problem and still you have time for questions. I hope you like it, yeah? It's kind of like, I think it's like smooth, kind of, yeah? The discussion is smooth. I don't know. Maybe I'm wrong. I might make a mistake. Brian. Yes, AJ?
So when you're taking derivative of the velocity function, wait, never mind.
Okay. Thank you. That was fast. Yeah. Sorry, sir. I'm not only blind a little bit, but I'm also a little bit deaf. Can you please volume up? Yeah, can you speak up? Oh, here. You mean here? Yeah. Here. Look, this guy, this green guy, is here. Okay, and this purple, no, orange, is here. Yeah. So instead of y, I have y at Vmax. Yeah. Okay. That was the question. Okay. Okay. Example number 2. Let's do it. We have 27 minutes, guys. So we will see, okay? Let's at least start it, okay? It's tough at the end. Okay, please familiarize yourself with the problem statement before we start our solution. All right, so what do we have in here? Right now, in the previous problem, we had one body only, one mass. In here, we have two masses, yeah? Two bodies. So we will draw two free body diagrams, by the way. We have mass of body A and mass of body B. Body A is trolley, body B is crate. By the way, we will in this problem, it's okay to model the crate as a particle, yes? Probably because they ask us what happens at this time instant only, okay? Only right now. Not what happens always in some period of time, yeah? They just ask us what happens right here, right now. That's why it's okay to model the crate as a particle. And we're gonna do it. Okay, so we have geometry. Yeah, our bodies are connected with a cable, AB, and we are on Earth, so we know gravity. We know that our trolley has this green acceleration. I call it A star, and we know its value. It's 1.2 feet per second square. We know how much is the incline. It's 25 degrees. We know how much our bodies weight, 40 and 50 pounds. And important information, our system is at rest. Very important information we will use later. And what else? Aha, there is also, so they ask us to find something interesting. They ask us to find acceleration relative. Yeah. So if you are this blue person here, yeah, if you're this blue person and you sit on the crate and travel with the crate, not crate, trolley, sorry. When you travel with the trolley, they ask us to tell them what relative acceleration you will see when you look at the crate. This is this part. Okay, so this will be for the blue person here. And also they ask us to find what is the tension in this cable that pulls the trolley up, that red T. Wow, a lot of things to do, guys. Any questions to the problem statement? So let's solve it, okay? And I'm not going to surprise you. We are going to start with free body diagram. However, maybe before that, let's write that sentence. We have two masses. That's why we should draw two free body diagrams, okay? We have two masses. That implies we will draw two FBDs. All right. So let me start with the first one. FBD for crate. And also KD. So our crate will be represented with a particle here and here. And these are the forces acting on our crate. This crate. So I believe that we have mg, big M, yeah? Because this has capital M. mg, and also we have tension in that cable. F. Okay, so I'm going to put it here. Are there any other forces acting on our crate? That's all. Only two. Okay? And let's right now define our inertia forces. So we will have big M A Y and big M A X. By the way, can you guys tell me what is the value of AX right away? Why? Perfecto. There are no forces acting in this direction. Do you see? The only forces acting on our crate at this time instant only. Not later. Later there will be forces acting in this direction, yes? But at this time instant only, the only forces that are acting on our body are vertical, yes? Yeah, perfect. Okay, we are done with FBD and KD. Once again, just for the last time in the semester, F equals to MA. Yeah. Second step of our solution is EOM. Second step is EOM. So let me do it quickly. Forces along the x direction. This is positive direction. 0. Yep. That's why MAX is. Oh, sorry. Oops. That's not true. That's why this guy is 0. Yep. This implies that our AX is 0. And now sum of forces in the y direction, and this is positive direction. And in here we have F minus mg. And this is equal to, oh, not a small one, big one, M AY. Okay. I just like when the equation signs are aligned, you know. Okay, so we have one equation here, yes? Let's look at it. So we have for sure one equation. And how many unknowns? We don't know acceleration, and we do not know the tension in that cable AB. Shoot, we have two unknowns. Yeah, not good. Solvable or not? Not yet. Yeah, so we need more equations. Yeah. Okay. However, before finding more equations, we have one more information. Remember, guys, that our A crate, yeah, or AB has only y component. Yes, it has AYJ. Yeah, because this guy is 0. This is very important information for us. We know that our crate will accelerate upwards. Okay? So we know actually two information. Okay, so now let's look for more equations. FBD for trolley this time. For trolley and also KD for trolley. Okay, what do we have here? So I'm just gonna draw that trolley, okay? It will be a rectangle like that. This rectangle, and exactly the same rectangle here. So I'm gonna start. What forces act on our trolley? I believe that gravity acts on our trolley. I like simple things, you know, mg. Any other forces? Do you wanna let me know what forces act on our trolley? Excuse me. Freight acts on our trolleys through the cable. Yes. So that would be F. Yeah. This F is exactly the same as this F, by the way. They just have opposite directions. Okay, they just have opposite directions. Yep. Okay, any other forces act on this trolley? Yes. So this T. And there's one more. Kevin, do I go for it? Or not? Perfect. And which direction? Perfect, exactly. Yeah. It must be perpendicular to that track, to that beam. Yeah, exactly. Normal force. Okay, anything else? I don't think so. Yes, Trevor? No friction. They didn't tell us anything about friction. Yeah. Okay, so we're done with FBD. Now let's express our motion. I propose in this coordinate system maybe. P and Q. Okay, so let's introduce our positive directions. So we will have small m AP and small m AQ. By the way, what is AQ? Can anybody tell me? What value will AQ have? Sam. Yeah. Okay, I heard a little bit of impatience in your voice. I will speed up. Okay, no. Yeah. You don't want to mess up with me, man. You don't want to mess around with me. Okay, just for the future reference. Yes, Sam is right, because this is our trajectory. Trajectory. Yeah, you can see, guys, that our trolley cannot leave this trajectory. It has to go along that line. That's why AQ is 0, which simplifies the equations, by the way, tremendously. Okay, we're done with FBD and KD. Second part is EOM. So I'm going to write sum of forces in P direction, and I believe that that was positive direction, yeah? So what do we have in here? Aha, we have T, and oh no, we must do some projections here. Oh no. Okay, so for sure we have T acting, but we also need to project mg and F on these two directions. Okay, so I need first to project mg on this direction and on this direction. And I believe that theta 25 degrees, theta is here, yeah? 25 degrees. So I believe that theta will also be here. So this projection is mg sine or cosine? Have one more guess? Perfect, yes. Cosine theta. And this one has no other choice, and it will be sine. Okay. And now projections of F, there will be orange. And they are analogical, they are analogous. Yeah, F, this is F cosine theta, and this guy is F sine theta. Perfect. Now we are ready to write down our equations of motion. So we have T acting in this way, and oh, these two guys act in a negative fashion, yeah? So in here we will have F sine theta minus mg sine theta. And this is equal to MAP. I'm going to do exactly the same on the Q direction. FQ, sum of these forces is N, minus f cosine theta minus mg cosine theta. And this is equal to MAQ. And Sam said that this is 0, and he was right. Okay. Questions so far? IJ? AJ.
How come the normal force like isn't in the opposite direction? Like when I thought it went like against the object.
Sure. That's a good question. So in I'm not sure if I'm going to say it correctly, but I believe that I am sure for sure. Yeah, am I? So okay, let me be on the safe side. In 99% of the problems, it does not matter which direction you put in here. Because I choose this direction, and imagine that at the end of the problem, our n will end up negative number. For example, minus 3.7 newtons. That means that it acts opposite way.
Yeah.
So in here, we just have a freedom to choose which direction our reaction force acts on our body. And if at the end of the problem, you obtain positive value for those reactions, that means that your guess was correct. That means that n indeed acts in this direction. However, if at the end of the problem, your value will be negative, that means that, okay, it acts opposite direction. Okay?
And how did you figure out that it was sine theta for the p direction, not cosine theta? I kind of missed that part.
AJ, this is second year of university, yes?
Yeah.
Yes, office hours. No, it's high time for you to finally figure that out. Really? No. Office hours, totally, yeah. And please don't hate me for what I said, yeah. No way. Office hours or just, I don't know, review notes from some other course. I don't know. Yeah. I don't have time for that right now, okay? Yeah. I'm sometimes harsh, sorry. Anyway, other questions? Yeah. High time to learn that, yeah, don't you think? Okay, guys. So I solved that problem yesterday, and I figured out that actually this equation does not matter. This equation, and I wanted to use green thing. Yeah. Yeah, I am for higher education, AJ. I'm for higher education. Yeah. So at some point, your instructor should So I will lead you. I will take your hand. I will lead you a little bit, through the problems. But at some point, I will leave you alone. Yeah. And you should sometimes invest your time in learning. I am for that. Yeah. You don't have to agree with me. I am for that. Yeah. I think it's more beneficial. Yeah. Just I told you earlier. I treat you guys like adults. Yeah. I treat you like adults. Yeah. Okay, so yesterday I solved that problem, and I realized that this equation does not contribute anything to our solution. This equation does not contribute anything. To our solution. We'll just leave it here, okay? We just put it together, but we're just not going to use it at all. We're not going to use it at all to our solution. Okay, but the first one contributes a lot. Okay, so let me recap. Okay, so we had earlier we had one equation here, and now we have this equation. Yeah, so I think we're looking for one more equation. Yeah, and let's just hope that we didn't introduce any other unknown. So we have two equations, definitely, and let's see how many unknowns. We have f, ay, and unfortunately, I believe that this is our unknown. Dang. So we have two equations and three unknowns. So what now, guys? Is it solvable? No. We need more equations. And that was the moment when yesterday I had to think for half an hour. Yeah. Okay. Thank you for that smile. Yeah. Yeah. I really didn't know what to do next. Yeah, I knew that I have to find third equation, but it took me half an hour basically. Any ideas, guys? Yes, Trevor?
Relate AY to AP.
AY to AP. Yes, okay, you are faster thinker than me. Of course, we have to. Because it's written here. We must use the relative motion. Yeah, and it took me half an hour to notice that. Yeah, I was reading this part for like 7 times, and it was like, in the font size 100. Written here, yes. Yeah, that I should go for this one. Exactly, yeah. By the way, they also wrote it in the problem state, in here, in the question, yeah, to the problem. They said that we should find this one. Oh, sorry. I know what happened today with me. You see, they wrote it here, just find this thing, yeah? And I was like thinking what I should do next. Of course I should go for relative motion, yeah? Okay. And now the monster part comes to our solution. Okay, guys. So this is the most abstract part of the problem, okay? So please, I don't know, like concentrate or do whatever you want actually. Okay, so now we're gonna find third equation, yes? And we're gonna go for relative motion. Relative motion. And so in other words, let's find ABA. And in my opinion, I mean, I should not share my opinions, yeah? But my opinion, it is tough to find it. Yeah. So I'm gonna steal that drawing. I'm gonna steal this drawing. And I'm gonna simplify it. I don't need that T, I don't need this, I don't need that. And that blue guy can stay here. Yes, it can stay, he can stay. And we don't need that mess. Okay. So what I would like you to think about is when you are this blue guy, okay, and you sit on the trolley and you travel with the trolley up the incline, yes? You travel with it. And you look at the crate. What trajectory you will see? What trajectory you will see, okay? So maybe, let's imagine that you are that green guy here. Yeah, that green guy is a stationary observer, okay? And if that guy looks at the crate, he will see such trajectory, I believe. Yeah, I believe so. That guy, maybe I exaggerated. He will see something like that. Yeah, this will be trajectory he will see. This is the trajectory of point B seen by that guy. Do you see my point? Yeah. So now don't be that green guy, be that blue guy. If you are sitting on the crate and travel along with the crate and you look at the crate, what trajectory you will see? What relative trajectory you will see? Think about it, okay? I will just write down that question on the board. What relative trajectory you will see? What relative trajectory? What shape of the trajectory? What shape that trajectory will have? Anybody? Brian?
Is it like a pendulum?
Is it like a pendulum? Pendulum is not a shape. Yeah, so what's the shape of parabola? Okay. It will be a straight line. It won't be a straight line, no. But he's closer.
Would be like a sector of a circle.
Yes. Like a circle. Yes? It is a circle actually. Like a circle, it's not a shape. Circle is a shape. Exactly. Thank you, Brian. You see? Yeah. It will be, yeah, because this is like a pendulum. You said you were right. This is a pendulum, yeah? it's not. So if you sit on the trolley, the thing is just moving like that with a constant radius. Yeah, it is a relative trajectory. Is a circle. Yeah. 4 more minutes. Okay. So that was the most abstract part, guys. Okay. So this is circle, and this is relative trajectory. So next part is to include this coordinate system. UN, relative, of course, and UT. Let's do one more step, and the rest I will finish at home, okay? I will share the video with you. So I would like to express our relative acceleration in this coordinate system, okay? So I would like to have A, B, A, N, and I would like to have A, B, A, T. So we will have here V rel dot UT rel plus V rel squared rho UN rel. Yeah, this is what we learned last Friday. Yeah, this is our acceleration. By the way, system starts from rest or not? It did. They told us that it starts. So velocity is 0. This velocity is 0. So that means that our ABA has only one component. ABA is AT rel UT relative. So in other words, I can erase this guy from this drawing. I can erase this vector. Okay, and the next step I see you drew, yeah. The next step is to write this thing. AB is equal to AA plus ABA. And observe that these 3 vectors are expressed in 3 different coordinate systems. And we will have to bring it to one coordinate system. However, we don't have time for that. I will do it in the video, and I will share the video with you, okay? Are there any questions? Wait, I still have you for 60 seconds, and there was a question of Drew.
Wait, can you explain again why that V rho squared over rho is 0?
Oh, because it starts from rest. It starts from rest.
Oh, okay.
Here. So if you see information that something starts from rest, every single velocity is 0. Every single velocity is 0, even relative.
And so why is the other one not 0 then? V rho dot rho?
Yeah, this is acceleration.
Oh, okay.
This is, yeah. And you, sir? Yes? Exactly, that's why. Plus, we model the crate as a particle. So it's only the cable, yeah. It's like a rigid cable. Yeah. Yes. Correct. Okay. Thank you so much and enjoy your weekend, guys.